Have you ever wondered how it's even possible to get high-speed internet from a dish the size of a pizza box, beaming a signal to a satellite hundreds of kilometers up in space? Well, it's one of the most incredible engineering feats of our time, and we're about to break down exactly how it all works.
So let's just start with the central challenge, because it sounds completely impossible. Starlink satellites are whipping around the Earth at 27,000 kilometers per hour. I mean, that is just unbelievably fast. So how in the world does a stationary dish on your roof hit a tiny target moving that fast from that far away? That's the big question we're going to answer. Okay, first things first, we need to be really clear. This is not your parents' old TV satellite dish. A TV dish is totally passive. All it does is catch a signal that's already being broadcast. But the Starlink dish, lovingly called Dishy McFlatface, is an active two-way communicator. It has to send and receive a super focused beam of data. And that, my friends, is a whole different ballgame. All right, let's dive into the first huge problem, that 550-kilometer gap. That is an enormous distance to send a wireless signal. So how can a relatively small dish generate a signal powerful enough to reliably punch through the atmosphere and reach a satellite way up there in orbit?
Well, one tiny antenna just isn't going to cut it, not even close. The signal would be way too weak by the time it got there. A good way to think about it is like trying to see a single bare light bulb from the International Space Station. You wouldn't see a thing. So somehow, Starlink has to make its signal thousands of times brighter.
The secret sauce lies in a really cool physics principle called constructive interference. The basic idea is, if you have a bunch of waves and you can get them to line up perfectly, so their peaks match up with other peaks and their troughs match up with other troughs, they don't just add up, they combine to form one single, much more powerful wave. So how does Starlink do this? Well, it's because inside that dish isn't just one antenna. Oh no, it's a massive grid, a whole army of 1,280 individual antennas, all working together as a team.
And this is where it gets really clever. You can see it here. Each of those 1,280 little antennas sends out its own weak signal wave. As all those waves travel out, they start overlapping. And through that magic of constructive interference, they add up in one very specific direction, forming a single, super focused, and really powerful beam. This whole process is called beamforming.
Now get this, because this is the really crucial part. Combining 1,280 antennas doesn't just make the signal 1,280 times stronger. Because of the way they focus all that energy into one spot, the final beam is actually 3,500 times more powerful than any single antenna could ever be. And that is how you bridge that 550-kilometer gap.
Okay, so problem one solved. We have a powerful beam. But now, for challenge number 2, that satellite is just screaming across the sky. You can't just point the dish and leave it. So how do you aim and track a target moving faster than a speeding bullet without any moving parts? The solution is it's pure genius. Trying to physically move the dish with motors would be clunky, slow, and would probably break down all the time. So the secret isn't to move the dish at all. Instead, you electronically steer the beam itself. And they do this using a technique called a phase shift. What that means is, instead of sending the exact same signal to all 1,280 antennas at the exact same time, you introduce a tiny, perfectly calculated delay to the signal going to each one. That little timing difference is the key to everything. This visualizes it perfectly. Look on the left. When all the antennas send out their waves in perfect sync, that combined wavefront just goes straight up. But now look at the right. By adding a tiny delay from one antenna to the next, the whole wavefront actually forms at an angle. It's incredible. By constantly adjusting those tiny delays, the dish can steer the beam across the sky, tracking that satellite perfectly. So we have a powerful beam, and we can aim it. We're almost there. The final challenge is the data itself. How do you take something as complex as a 4K movie and actually encode it into that radio wave? How does the signal carry the information?
Here's the thing to remember, that data isn't just sent along with the signal is the data. The message gets encoded by making incredibly fast, subtle changes to the wave's most basic properties, its strength, which is its amplitude, and its timing, which is its phase.
They do this with a method called quadrature amplitude modulation, or QAM. Now, that sounds complicated, but here's a simple way to think about it.
Imagine you have just two levels of signal strength, let's say low and high, and two different timings. That gives you four unique combinations, right? You can see them here. Each one of those combinations can represent a little piece of binary data, like 00 or 10. Starlink uses a much more advanced version with 64 different combinations, which lets it pack a ton of data into every single signal. So, by switching between those 64 unique states millions of times a second, Starlink can cram an absolutely enormous amount of information into that beam. And what's the result? A data transfer rate of up to 540 million bits every single second. That's how you can stream multiple HD movies without a single hiccup.
Okay, so let's step back and put all three of these amazing solutions together, because when you see it all at once, you really understand how this new global connection is being built.
So let's recap the three magic ingredients here. First, you've got beamforming, using that army of 1,280 antennas to make the signal 3,500 times stronger. Second, phased array steering, which electronically aims that beam at a speeding satellite. And third, data modulation, which packs that beam full of hundreds of millions of bits of information per second. And what does all that technology get you? A signal leaves your dish, travels 550 kilometers straight up into space, and hits a satellite in just 2 milliseconds. The speed is it's almost hard to wrap your head around. This technology is weaving a web of connectivity around our planet unlike anything humanity has ever seen before. So I'll just leave you with this to think about. As this network of thousands of satellites continues to grow, blanketing pretty much the entire globe in high-speed internet, what does it really mean for all of us, everywhere, to be truly connected?